Okay, so we were discussing photolithography, and this is a meaning lithography, yeah. So it's a very important process for fabrication of devices. Okay. So the basic idea is already described, right? What you want to do, what are you trying to do, and how this is being achieved. Okay. You know, if you look at the cost of setting up a manufacturing line for making integrated circuits, one of the most expensive part of the whole thing is actually the photolithography system. Yeah, but so it can be very complex and very precision equipment. You can see that the systems, you are talking about very small features, right, that you want to print here. Okay, so we'll see some implications of this in the next coming slides when we define the basic parameters of lithography. So this is, but on the other hand, you can also make your own lithography system. Okay. It's not very difficult, because in the sense that you know, in olden times, maybe 10 years ago, I used it for making my MTech presentations. Okay, we used to have the slides, not the projector, right? Yeah, so the transparency slides, and you print your things on the transparency sheet. This is plastic transparent sheet. Okay, and then what do you have? Is like a lamp, yeah, and then so you have some diffuser glass which will actually make the illumination uniform, okay, and then you place your transparency on top of it, okay, and then light comes through, and then there is some lens which will actually capture this and then project it onto a screen like this, okay. So this is exactly same way you can also make a lithography system. You need a mask through which light goes through, and then you project it onto a plane like this. Yeah. So it's not very difficult. That's what I wanted to say. So one of our colleagues, for example, Professor Narasimhan, I don't know if you know him, very senior faculty member in our department. He has made this kind of things which students are using in the lab. Yeah, so if you want to make, you know, 10 microns, 5 micron devices, this is not a difficult task. Okay, so it is possible to make this. Okay, so but then you also want to make very small dimension devices, but also with very high throughput. So there are other challenges that come in, and the optical part which we have discussed is not the only thing, okay, but we will see some of these details going forward. So you can see that the light sources or excitation sources that are used in lithography traditionally had been this, so what is called G line, so that is wavelength of 436, and then so used mercury arc lamps very commonly for this, and then 365 nanometer was the next one, and then 248 was the next. And then you have 193 nanometer lithography. Okay, again laser, and then you can see using water as the medium. Okay, instead of using air as the medium. Yeah, and the next is, meaning maybe some this may come into the picture, extreme UV, so where the wavelength is very small. Okay, and then the next, of course, E-beam is very widely used for small volume production, making masks, okay, and also for R&D purposes. So why is the wavelength important? Okay, so we'll see that later on. So the lithography systems, the minimum features that you can print are limited by diffraction. Okay, so we'll see that in a short while. Now, yes. So you can actually, the water has higher refractive index than air. Okay, so that helps you to design lenses which can have what is called a larger numerical aperture. Okay, so that is the idea. So we'll see this, these kind of details. So now the wavelength comes very often when you talk about light. Okay, so when we talk about electromagnetic radiation at lower frequencies, right? You talk about the frequency, not really the wavelength. Okay, but also we sometimes say things like millimeter waves, but otherwise we are talking about megahertz and maybe gigahertz, right? But when you talk about light, people use wavelength. Okay, and then for electronics, it is important to correlate this to band gap. Yeah. So just a very simple thing, right? You can write this energy is equal to h nu. Nu is the frequency. Nu is equal to, or what is then? So I can actually write this as c by lambda, right? Nu is c by lambda. So hc by lambda. So E is equal to hc by lambda. So I just rearrange this. So you get this lambda hc by E. H is the Planck's constant, C is the velocity of light, and these are constants, right? Meaning you're looking at vacuum, so velocity of light is constant. We know that value. So you substitute these numbers, and then you can get a very simple equation. This is easier to remember than actually doing the calculation every time. So you substitute the value of H and C, and then you get this equation. Lambda is equal to 1 to 39. So you just take it to the nearest multiple of 10. 1240 divided by E in electron volts. Okay, that gives you lambda in nanometers. Okay, so this is a very simple thing, that people, when they talk about, so I have a semiconductor, this absorbs at this wavelength and so on and so forth. So you just quickly calculate, right? You can do these mental calculations. 1240 divided by the band gap, or the other way around, right? You take the lambda on the other side, you get the corresponding band gap. Okay, so you can quickly tell me, for silicon, what would be the wavelength below which light will be absorbed? Pardon? Yeah, but you can still get, if you look at the absorption as function of wavelength, it drops. So only thing, how much light will be absorbed, right? Or the distance over which it gets absorbed is going to go up. But still beyond a certain wavelength, silicon will not absorb. So what is that critical wavelength? Okay. Huh? Very simple, right? You have 1.1240 divided by 1.1. Okay. 121 is equal to 11 square. So you get this as roughly 1100 nanometers. Meaning, yeah? Immediately got. So this is very easy. So just this number is easy to remember. What do you know? What is the value of H, by the way? So you need to do this calculation. You have to remember two numbers and then do all this calculation. This is much more simpler. Okay. So this is a very important thing. You can see that this is what is a part of what you call the expertise. Yeah. as you do things again and again, you actually find all these simple shortcuts and easy ways to find things. And when you are attending a seminar, for example, that person, expert, is not going to explain what this means and so on, right? He just shows this absorption curve. Immediately you should be able to calculate, oh, what is the band gap of this material, for example. Yeah, you don't have to, and they may actually present wrong results also sometimes, right? Sometimes you go and make a presentation, seminar presentation, and then the examiner asks, no, that number is not correct, because you're wondering on what basis he is saying this, right? So these are things that can be done very quickly, easy things. Okay. Okay. Now, what is the problem? So if you look at this, you can do a simple calculation. What is the energy that you're talking about for this photon? Just do a quick calculation. What is the energy that you are talking about? So 1240 divided by 13.5. So it's close to 90. Yeah, meaning 100, close to 100 electron volts. You tell me a material that has a band gap larger than 100 electron volts. So what is the problem? What is the problem? If I want to use this for lithography, what is my problem? So if I want to make anything, a lens, for example, to focus this, okay, what material would I use for making that lens? What is the problem? What is the property that it should meet? The lens material should not absorb the light. It should come through, right? Yeah. If it absorbs, it actually is, it's opaque. So if you use glass, normal glass, or quartz, the band gap is 9.1 eV or something. So that would actually, look dark, right? Meaning, if you look at it from the other side, of course, our eyes will be spoiled by this. I think, of course, yeah. So there are no materials like, you will need a vacuum. First of all, even air would actually absorb. So all these molecules, atoms in air would absorb this EUV thing. Yeah. So you can see, if you look at the solar spectrum measured on Earth, so there is a drop below 350 nanometers. Yeah. And then 180 and so on, it actually drops down drastically, because oxygen, all things actually absorb UV radiation. And it's good for us, because that is why UV exposure, heavy doses is not good for our health. But we should, of course, have some, because a lot of things in our body happens because of chemicals that our body produce by using this UV rays. For example, vitamin D, for example, is synthesized in our bodies, and we need a little bit of UV. Okay. Electron beam, of course, if you want an electron beam and you want to steer it around and so on, it has to be in vacuum. Yeah. So A-beam systems are by definition vacuum. E-beam, the one thing is that there are charged particles, so you can actually use magnetic fields and electric fields to focus and steer them. Yeah. So EUV is not that easy. Okay. So this means that, you are talking about, I had some numbers. Let me see here. So I think there are technologies already, some people have developed these things, but not in commercial use, because of the huge cost involved in the extreme UV systems. Okay, lithography mask. I wanted to show you something I have, but this is a simple mask that somebody has made for some applications, or glass plate with chrome or you can also, as I mentioned, you can print it on transparencies if the dimensions are not very small. Okay. So the basic material is transparent to light or whatever material that you're using. So for electron beam lithography, you can't use a glass as a mask. There it is rather easy because you are actually going to steer the electron beam, which is focused, right? So you are actually going to use an electric field, or maybe you fix the electron beam and then move your plate, yeah, whatever the substrate. Okay, so that is fine. That is why actually the electron beam lithography takes a long time. Yeah, unlike the light optical lithography, where you just turn on the light for few milliseconds, maybe, or seconds, and then the whole wafer or substrate is exposed to it. And the opaque layer, very common for optical lithography, would be chrome. Iron oxide is also one of the very commonly used thing. And then black ink, if you want to print it on transparency sheets. Okay, so this mask is very important because for every stage of patterning in an IC, you would actually have to make a lithography. Okay, except for selective epitaxy, if you use it, right? Except for that, every other selective process, right, where you want to etch something, yeah, or you want to do implantation only in select regions of the wafer, you need to precede that with a lithography step. So you can see the mask is very important, and if I make a VLSI chip, right, you may actually have close to or more than 100 masks used for making this chip. Okay, and you can see again the one of the end result of your VLSI design is actually a set of masks. Yeah, so you may have a simple inverter, but that's not. So you can draw this like I have an inverter. Right, this is your inverter and it goes out, VDD and so on. So you can actually now okay, this is your you're going to do all kind of analysis, but the end of it you need to tell people how they should be laid out, right? What are the dimensions, how they should be actually connected together, and so on and so forth. Okay, and how this has to be connected together. And all that information actually is given to the manufacturing stage through a set of masks. Okay? Now there are two types of resist. So this is now very important. We talked about the light and the lenses, but what is there on your substrate would be a material that is sensitive to this excitation. It can be electron beam, it can be photons. So that's called a resist. Okay, so it actually resists something. Yeah, so we will see why that name. But you have a substrate, and this is your resist, and this is your mask. And let's say this is an optical lithography. So this region is transparent. Okay, so light goes through this region. So this part get exposed to the light. Okay. So you have this part exposed to light, and then you develop the resist. So that you can have two types of resist, and in one case this is called positive resist. So you're actually trying to remove the photoresist selectively. If it is a positive, you started with a positive photoresist, the exposed regions can be easily dissolved in the developer. Okay, so this is removed. And if it is a negative resist, it actually remains. Okay, so this part remains. Okay, So these are two different types of resist that you use. Now, if you look at the specifications of a photolithography system, there are these are the parameters of interest. So this is called resolution, the smallest feature that can be printed. Okay, so what is smallest size feature that you can print? Okay, and when you say print, what do you actually understand by this? So is it the smallest feature that I can get from my optical system or on my wafer? Because if I am actually talking about the optical system, the resist is not in the picture. Okay, but when I talk about the feature on my wafer, then the resist is very important. Okay, so when you talk about lithography, you need to actually learn about both the things. So basically, we'll see this in this module. What are the important parameters? What are the characteristics of photoresist? We'll not go into a lot of this photochemistry. If you're interested, you can actually look at this book by, so this is in this book by, so Plummer's book, right? VLSI technology. It's not very expensive, so anybody is working on device fabrication, I would recommend you to buy this. There is an Indian edition that is available. So resolution is the smallest feature that can be printed. Actually, you can print any small size, but that is not important. You should be able to recognize this as a feature. Okay? So we'll define this later on. What are the considerations for defining this? Pitch is something relates to the smallest spacing between the features. So we'll see that in a moment. Okay. Overlay is alignment accuracy of a layer to the previous layer. Okay. So again, we'll see this. Throughput is something that we may not discuss further. How many wafers can be processed per hour? This is a very important consideration for manufacturing. And then again, this is also very important. Defect density. So this refers to the defects generated on the wafer per unit area by the lithography process. Okay. So usually this defect density is important from the point of view of lithography itself. Okay. So if you are doing a lithography process, and that leads to some deposition of particles on the wafer. Okay? Yeah. So what would happen in the lithography process? So during the exposure, for example, some particles fall on the wafer. What would happen? Huh? They will actually modify how much light goes in. Right? So, because I have a photoresist and I am exposing this to light. And from the lithography system itself, the particles falls on the photoresist. Okay. Yeah. Now, the optical properties of this piece and what are the dimensions would actually influence how much light the photoresist actually receives. Okay. So then I may not have, so which will then mean that the defect that is generated would have an influence on the final features that I get on my wafer. Okay. So very important consideration for lithography. So we'll see that, briefly discuss it in the next slides. So critical dimension, if you say this critical dimension is smallest. So if I actually look at some parallel lines, very simple case, okay, and you can see the smallest size that can be printed. Okay. Now, one very important thing that we should consider is that suppose I have this, okay, this parallel lines, and I have a single line, isolated, far from other things. So the smallest feature size I can print for an isolated line and a dense array of lines would be different, and the difference comes from the what? Diffraction, but that leads to what? Diffraction, yeah, but that leads to what? Diffraction is also present if I have a single piece, right? Just one isolated line. It will come from the interference of the diffracted light. Okay? So, when you talk about the critical dimensions, it's very important to make this distinction, because in a VLSI circuit, you want to pack the devices very densely. Okay? Very important consideration. Okay. Now, what is pitch? So, this is another consideration. Pitch is always, so if you have two lines, parallel lines, from this leading edge to the leading edge. Okay. So, you can see this critical dimension plus this. Okay. Now, very important thing that you think about it, pitch is, let us say I have very simple thing. Okay. These are two lines on my mask, okay, and then I printed this on the wafer and the photoresist, yeah, and after developing and so on, I got some features, and they look like something like this, slightly larger, for some reason, we don't know, okay. So this is what is on the mask, and I got something bigger on the wafer. What about this one? Can you draw? So the critical dimension on the mask is, meaning that the dimension on the mask is smaller than on the wafer. Okay. Yeah, so you see these dotted lines, right? Slightly bigger. These are the dotted lines, right? Okay. What about the pitch? Pardon? Pitch will reduce, increase, remain the same? Three options, right? Oh, I don't know. Okay, of course that is, I'm not giving you that option, okay? How many people say that it will increase? Time will come when you have to raise your hand. Huh? Only three choices. Okay, so they say, okay, who thinks that it will decrease? Okay, and will remain the same. Okay, so why do you think it will increase? Yeah, so this has increased, but I'm talking about the pitch. So pitch is defined as this, right? So on the mask, if you look at it, the pitch is this. So leading edge to leading edge, or lagging edge to lagging edge, whichever, trailing edge to trailing edge, right? So who said decrease? Yes. Can you explain? Huh?
The second one is also having a lateral.
Okay. So no, the spacing has decreased. See, if I actually draw this, right? So it goes up by the same amount. This would be same as this. Okay. So of course, but the spacing definitely has decreased. Okay. But the pitch remains the same because it has shifted. So it will now start from here to here. Right. Pitch remains the same. Okay. So the feature size, there are many ways, tricks to play to actually get your feature size very small. Yeah. So you can see people actually printing 20 nanometer lines using a 193 nanometer wavelength lithography. Yeah. Final feature on the wafer is 20 nanometers. That's possible. Yeah. But I can't reduce the pitch very aggressively. Okay. Because I can make it, there are, I can play with the resist. I have some other ways to actually, reduce the dimensions during the etch process and so on and so forth, which we will discuss later on, okay, in another module. But the pitch is much more difficult to scale. So we'll see some ways towards the end of this module, some complicated things that people do to actually reduce the pitch. Okay? Now, there is something called overlay. So, why this is important? We talked about 100 masks, right? And overlay is when I use a particular, yes?
Which is for the area where you're depositing one disk block. So, in a pattern, if you do that, then the spacing between them will be reduced, right?
Spacing is reduced.
So, whatever is coming in between or connecting or not connecting, that will have a less space.
Yeah.
So, for once it will not be reducing, but if it is happening, like the boundary is increasing, then next time you have to have a larger area to fit all those things.
Yes. So, this comes in what is called design rules. Okay. So, what he's saying is that, okay, these things are, in this particular example, this feature has become bigger than what you have on your mask. Yeah. So, you wanted to put something in between. So, now the area available to put that has shrunk. Yeah, valid point. Huh?
Why they are always considered the pitch?
No, I'm not saying we are always considered about the pitch.
Like spacing is the investment.
Both are important because you want to reduce the pitch because you want to put more devices in the same area of the chip. Okay?
Then why is it difficult to do that?
Huh? Yeah, we will see that. We will see that. Huh? We will see that. There are some very fundamental problems with this. Okay? Now, the overlay is a very important thing. Again, I would spend some time on this because this is where a lot of this traditional link between the design and the VLSI technology comes into play. Okay? But now that link has become much stronger because of other factors. Because you're pushing the devices to the fundamental limits that is possible with the physics that we usually consider, yeah, for the operation of those devices. Okay. So there's something called the circuit technology core design. You can't actually just do one without considering the other. Okay. But when I was doing my M.Tech, for example, this was the end of the story for a VLSI designer. Okay. You make the layout, so you have this nice circuit that you have designed, and you do the simulations using SPICE and make sure that it works, and there are some specifications that you have met, and then you create the layouts. Okay. And there are programs used for checking what is called the design rules, whether you comply to the design rules, right? And many a time the VLSI designer skills actually involved in what kind of circuit topologies are available to them for making different types of circuits, and then combining them and also quickly putting them together so that it can be manufactured without much failures. Okay? So that you need to know about the design rules and so on. Now, what is this? What is the layer 1, layer 2 and then overlay? Do you understand what is meant by this? What is it? Yeah, so you are talking about 2 layers, right, in the mask. So let us take a very simple example. I want to make a MOSFET. Okay, so I want to make a MOSFET. It looks like this. So this is my gate, and I have my transistor, something like this. I am actually not drawing all the details here. Yeah. So this is how you draw a transistor, right? Okay. But we need to worry about what happens in the other direction. So usually when you make a layout of the circuit, you are actually drawing what is seen from the top. Okay. But when you do your device course, you are looking at how it looks this way, right? Cross section. Yeah. But now if I look at this from the top, it would look like this. So this is my silicon, okay? It looks like this, right? Okay, this is a top view, okay? So this is my silicon exposed, and then I have my gate. Gate will be a strip like this, right? Yeah, got the point? So this is my, what is called the active area, okay? So if I take this, what is surrounding this? Isolation. So we have this shallow trench isolation and all these things, right? So around this would be oxide, and there is maybe there is another transistor here and so on and so forth, right? Immediate neighborhood, you have oxide, okay? And then you have a gate, okay? So I define this by using a lithography step, okay? Yeah, I make my isolation, and then I deposit my polysilicon implantation and all these things. I deposit meaning I grow the gate oxide, I deposit the polysilicon everywhere. I now want to pattern my gate, which will give me something like this. Okay. So I need to do a lithography. So that is the layer 2 in this example. Okay. So I don't have a red choke here. So, but we will. Okay. So it looks like this. Okay. So this is my gate, the layer 2. What is my problem with this? What is the requirement when I put my layer 2 on top? Pardon? Can you relate that to overlay, something that is given there? Huh? Suppose I have a misalignment and my gate ends here, for example. Okay. Will this transistor work? Okay, because I have this structure only in this region. Okay. Here I am going to put my gate and I am going to do source drain implants. So this will be N plus, this will be N plus, this will be N plus. This will be a resistor in parallel with a transistor, and the transistor is now useless. Okay, so this overlay is very important. Yeah, so the overlay is coming from how well you can align your present lithography step to the previous things which are already on your wafer. Pardon? Yes, so you have what is called an overlay budget, for example, right? So you can't get, they will say, okay, this may, the overlay error would be a certain number, okay? So ideally you may want to have your mask just like this, right? You may, if I'm really thinking a very theoretical guy, I may just think that, okay, this is fine, this transistor should work, but it would not work. Because you may actually, when you do this, so they may actually say, okay, 99.999% of the time, it would be within this range. You print it, right? May go this way or that way, but only, okay, this can also go this way, huh? That is also possible, yeah, in both the directions. Okay, so this is what is meant by overlay. So this is actually, we talked about one, I have one layer and then I want to align this to the next one. So if you imagine if I have to do this, okay, how would I do it? Hey, you think about, don't forget about all this lithography system. Do you have any situations in life where you have encountered where you have to align something to something? Huh? Yeah, so she's saying making some grooves, very important point, yes. Okay, make some grooves. Yeah, there are a lot of instruments where you can't put them in any way, right? Yeah, for example, if I take a plug, yeah, so there are 3 pins, and why this is not on an equilateral triangle and with equal spacing or with equal sized holes, for example? Why not? What will happen if I actually have an instrument, right? And the plug is like 3 holes at the corners of an equilateral triangle, and the holes have equal dimensions.
So then I won't be able to distinguish whether I'm using the main or neutral or the...
Yeah, so this is important, right? So is it, meaning I think that this is it should be earth, right? So I put it this way, and then I turn it on, right? Okay, hamara kaam. Ready for the mortuary, okay? So this is, there are, of course, this is not so fatal, okay? But, so you need to align things to what is already there. Okay, so it's very important. Now, how do I do it? It's very simple. So you have some markings on the, so these are called alignment marks. Okay, so if you go back to the previous slide, right? So you can see this crosses, very commonly used alignment marks. Very simple alignment marks. So you have it on the mask, but also this is, let's say, one layer. The next layer you would have exactly the same marks or something, yeah, that can be aligned to this on the next one, exactly at the same locations. Okay, so this is some possibility. Okay, so overlay is a very important thing because it actually decides, also a very important parameter that decides how densely you can pack things on a wafer. Okay. Now exposure systems, there are different types, and the applications. So there are some are very simple, okay, and some are fairly complicated, and their capabilities also vary. So these two are very similar. So you have a light source, right? Both cases. You have a lens, yeah, that will create what is called a collimated beam of light. So it's parallel beam of light, and then you have a mask, and there is a photoresist on the wafer, okay, and you keep the mask on the wafer, Yeah? So it is touching the photoresist, and you shine light through this region. Light will go through and then would lead to whatever photochemical reactions are happening in the photoresist in response to this. So this is called contact printing. You are actually making a contact between the mask, okay, and the photoresist. Okay. Now here you can see the diffraction is not going to have much impact. Okay. So if I have an edge that is diffracting light, right? So this is my point source, actually gets diffracted like this, right? Yeah. But you are putting your image plane right here. Okay. So closer it is, diffraction limits are, meaning effects are less. Okay. So the diffraction effects are less in this case, and it's a relatively cheap system. You just place it, you don't have to, worry about the spacing between this wafer and the mask and so on. You place it on the wafer. Yeah. And then, but there is some problem, defects, because the photoresists are usually soft materials. Okay. So it's usually a fluid, okay, a liquid, yeah, a highly viscous liquid, and then you are annealing this at 100 degrees centigrade and so on and so forth, and it can be very easily removed using organic solvents, okay, most of the photoresist. So it's a soft material, so it actually can stick to your mask. Okay, so that is called the defects on the mask. Then once you do a lithography, you may actually have some photoresist residues on the mask, okay, and how that has come on the wafer, meaning on the mask, they actually, during this process, some have come off your wafer, okay. So this can lead to defects on the mask as well as on your substrate. So I need to clean this mask, yeah, ideally after every exposure, okay. So it tends to be very simple, but then there are some disadvantages. Proximity printing, okay. Proximity printing is that the same thing, but you have a small gap. Okay. Now, if you want reproducible results, this gap should be the same. You get my point, right? If you by some mistake your gap is something like this, your feature is going to be. If the image plane is here, because the gap is larger, the feature is going to be so different, right? So maintaining this gap is important. Okay, so then it will be a little bit more sophistication is needed to control this gap. Okay, so you have defects not as much as here because you are not bringing it in contact. Okay, but it's so close, so sometimes you may actually inadvertently make a contact. Diffraction effects come into play because there is a gap, and then cost will be higher because it's slightly more complex. This system is different. You can see the mask is not in contact. Actually, you have a optical source, a lens to collimate it. The mask is right here. The image that is created, or the light that goes through, is actually again manipulated using another lens, and that is actually brought onto the wafer. Okay, so there are two lenses in this. So this is called projection printing. Okay, so you are projecting an image onto a plane. So there are no defects because there is no contact, right? But there will be significant diffraction related problems because you are taking this image and then manipulating it again using a lens. So there will be definitely diffraction effects, and obviously this is going to be much more expensive. Okay. Now in this system, one thing is that the feature size you get here would be same as what is on the mask. But here, is there any other possibility? Pardon? I can get a smaller feature on the wafer than what is on the mask, because I can use a reduction lens, right? Yeah, so that is possible. Okay. So if I want 100 nanometers, I need on the mask only. Even 400, if my lenses are good, I can actually project a 100 nanometer feature. That is possible. Okay. So this is a very important consideration. So a lot of this high resolution lithography systems for production for these reasons, no defects, and also you can actually do a reduction of feature size at the printing level. Because of these reasons, even though these systems are much more expensive, actually are preferred for manufacturing. Okay, high volume, small feature size device, integrated circuit manufacturing. Okay, we'll continue the discussion in the next lecture.